All right, here are solutions to part three, I guess, of practice test two. In this section, you are not allowed a calculator. And this is my third video. In this video, I'm going to be talking about problems 11 through 15. So in prior videos, I went over 1 through 5 here and 6 through 10 here. So in this video, I'll pick up with 11 here, where you're asked to divide complex numbers. And if you know how to divide complex numbers, you just go through and do it. The trick to dividing complex numbers is really what you do is you multiply by what's called the conjugate of the denominator, and I'll show you that in just a second. If you don't know how to do that, maybe you can kind of eliminate some options by figuring out why they put what they did. With fractions like this, you cannot break this up into 3/8 minus, I don't know, 5i over 2i or something like that. You can't break them up like that. That's not how these fractions work. So you can kind of see the answers that they put in. The test makers sort of put these two in there to allude to that idea. Those certainly aren't going to be the answer. If you don't know how to do this problem, you can at least narrow it down to the two of these guys. You might think that, oh, it has to be the minus one. It has to be c because of this minus sign here. Unfortunately, I don't think you can come to that conclusion this early. I think the denominator will have something to do with what this sign is here. So I don't know. At least you can narrow it down that way. But if you were actually doing it, what you would do, as I alluded to earlier, is anytime you're dividing complex numbers, you change it into a multiplication of complex numbers by multiplying by what's called the conjugate of the denominator. So the denominator is 8 plus 2i. The conjugate of 8 plus 2i is 8 minus 2i. All the conjugate is the complex number that has the same real part, but the imaginary part, you have to change the sign. So note that I changed the sign in between these two guys. It's not negative 8. It's still positive 8. It's just now it's minus 2i. Anyways, that's what's called the conjugate. When you multiply complex numbers by their conjugate, a nice thing happens. You get a real number. What I'm saying is 8 times 8 is 64, and 8 times negative 2i and 8 times positive 2i are going to cancel each other out. That's not coincidence. That's going to always happen. Then the 2i minus 2i gives me minus 4i squared, but I squared equals negative 1, so this is really plus 4. What I'm getting at is my denominator is 64 plus 4, aka 68. And the numerator, 8 times 3 gives me 24. 3 times negative 2i gives me negative 6i. Negative 5i times 8 gives me negative 40i. I'm essentially just treating the I like it were a variable, like it were an x or something. Until I get to this last one, negative 5i times negative 2i. Negative times a negative makes a positive. 5 times 2 gives me 10. So I have 10i squared. But instead of writing plus 10i squared, I'm going to write minus 10 because I squared is equal to negative 1. And now if you combine like terms, you got 24 and negative 10. So you have negative 4, so you have positive 14. Then you have negative 6i minus 4i, 40i, so you have minus 46i over 68. And so maybe you could have concluded that the sign in between them would be negative if you really thought ahead about what would happen when you're foiling things out. Well, anyways, if you could figure that out, more credit to you. But I couldn't when I first looked at it, so I went through and actually solved it, and I got here. At this point, I know this is my answer because it's got a minus sign in between the real and imaginary parts. But if you don't feel good about that, you can be like, oh, the denominator here are 34s, and this is 68. That's exactly twice that. Oh, right, they just reduced this fraction. Factor a 2 out from the top, you get 7 minus 23i, and then cancel that with the 2 from the denominator, you get all over 34, which you can break up as 7/34 minus 23 over 34 times I, which is what we got in answer C here. Number 12. Number 12, you're asked to solve for f in this thing. The reason I know that is not because I read this, but because I glanced at these, and each of them f is solved for in terms of r's and n's and such. The easiest way to do this is algebra. That's what I'm going to do. So the challenge to solving for f is there's two of them. There's one here and there's one here. So what I have to do is eventually get all the terms with f's in them on one side of the equation. But it's hard to do because this f is kind of hidden down here in the denominator. So I'm going to first get rid of the denominator by multiplying both sides by n plus f. So on the left-hand side of the equation, I have this r times the n plus f I just multiplied by. And on the right, I just have the f because the n plus f I just multiplied by cancels with this n plus f right here. Okay, so now you got f all by itself, but it's in terms of f. That's no bueno. You got to get this f over to this side of the equation. It's hard to do with the parentheses, but you can get rid of the parentheses if you take that r and distribute through. It'll give you rn plus rf is equal to f. So then to get all the terms with f's in them on one side, just subtract that rf, maybe over to this side. And now all your terms on this side have an f in them, so you can factor out an f. And what you'd be left with is 1 minus r. Don't forget to write the 1 right here. The way you can convince yourself you need this 1 is if you took this f and distributed it back in, you'd need this 1 here to create this f. Anyways, you get here to solve for f, just divide by the 1 minus r stuff, and you get f is equal to rn over 1 minus r, which looks like b. So b would be my answer. If you refuse to do the algebra, I suppose you could pick numbers, like if f equals 1 and n equals 2, then r has to equal 1/3. And try plugging those in 4 times and seeing which one gives you a true equation. And hopefully you only get one that gives you a true equation down here. If you got more than one, you'd have to try new numbers in here. So not an ideal way to solve this problem. It's better just to do the algebra. 13. Okay, 13 is tricky. Well, kind of. What is the sum of all values of m that satisfy this equation right here? Oh, it's a quadratic, right? I have to factor. It's easier if the leading coefficient is a 1. How convenient. These are all even numbers. I could divide both sides of the equation by 2 and get m squared minus 8m plus 4 equals 0. And now I try to factor. Unfortunately, you'll probably have a hard time factoring. When you're trying to factor, what you're looking for here and here are two numbers that multiply together to give you 4 and add together to give you -8. You're like, there are no such two numbers. Actually, there are two such numbers that make that happen. But they're hard to come by. They're hard to think about what they're equal to. They're not whole numbers, for example. They're not integers. So you might give up on factoring at that point. In fact, you shouldn't, because the question is not asking you to find the roots, to find the solution. It's asking you for the sum of the values satisfying this thing. So if this did factor into, I don't know, maybe I'll call it, what's a good letter? A and B. Right? If this did factor like this, then what that would mean is a plus b equals this -8 right here. But a and b would not be my solutions, right? I take m plus a and set that equal to 0, and m plus b and set that equal to 0, and I get my solutions are -a and -b. So really I would have that a plus b equals -8, but my answers will be -a and -b. So if you ask me the question, what is the sum of my answers? What's -a plus -b? I would say that's the negative of -8. In other words, my answer is D here. It's 8. Yeah, you probably wouldn't think to do that, right? I mean, maybe now you would that you've seen this problem. So if this exact problem shows up, you're good. And the hint was you weren't looking for the answers. You were looking for the sum of the values that serve as answers. But what I suspect most people would do is they'd get here, they'd be unable to factor. So they'd be like, all right, quadratic. My solutions are x equals -b. So a is 1, b is -8, and c is 4. -b plus or minus the square root of b squared minus 4 times a times c, all divided by 2 times a. So my answers are 8 plus or minus the square root of 64 minus 16. This is getting to be a bit much without a calculator, but fine, is equal to 48 over 2. So these are my two answers, right? 8 plus this and 8 minus this. But look, if I add those together, if I do 8 plus root 48 over 2 plus 8 minus root 48 over 2, what I get is 8 plus root, it all has the same denominator, so I can just add them right up. And the root 48 and the minus root 48 end up canceling each other out. So I just get 16 over 2, which is my solution, 8. So you can get there using the quadratic equation, which is probably the way most people would solve this. There's a shortcut, fancy way to do it if you're really clever here, but I suspect most people wouldn't think to do that. 14, a radioactive substance decays at an annual rate of 13%. So the way you can think about it is after each year, 1 minus this, in other words, 87% is still there. 13% is gone, 87% is still around. If the initial amount of the substance is 325, which of the following functions models the remaining amount of the substance t years later? So the way to think about it is right now I got 325. Next year, I'll have to multiply this by 0.87 because I'm keeping 87%, I'm getting rid of 13%. The year after that, I'm going to have to multiply this by 0.87 again, and then 0.87 again, and then 0.87 again. Every time a year passes, I have to multiply by 0.87 again. In other words, I'm going to raise it to the t power. That's what you get for answer A here. I suppose if you really wanted to, you go plugging in numbers. Be like, all right, after 1 year, how much would I have left? Maybe after 0 years. I mean, you can convince yourself that neither of these answers work. If you just say, well, after 0 years, I should have 325. I should have what I start out with. But if you change t into 0, this answer is 0.87 times 1. And this is 0.13 times 1. So neither of those can be solutions. So it's got to be one or the other. And since you're decaying at 13%, you're keeping 87%. A ends up being your solution. All right, 15. This expression is equivalent to which of the following? So I kind of like this problem. I don't know, maybe I shouldn't admit that. This is a number, right? This is equal to the number 1. This is not equal to the number 1. How do I know this is not equal to the number 1? Well, because for a fraction to be equal to the number 1, the top has to be the same as the bottom. The top here is not the same as the bottom here. I have 5 of these x's here. I only have 1 of these x's here. This can't possibly be the solution. This is also a number. It's just not equal to the number 1. This also cannot possibly be the solution because I cannot cancel out all of my x's. The reason I can't cancel out my x's is because the numerator here is not a multiple of the denominator, right? This x term is 5 times as big as this, but this is not 5 times as big as this. If this were 5x plus 15, then I could factor and cancel out, get rid of all my x's, but it's not. The top's not a multiple of the bottom, so there's no way the answer is equal to a number. B can't be my answer either. So it's got to either be C or D. Well, look, what you can do with these is you can make it 5x over x plus 3 minus 2 over x plus 3. Note that looks a lot like C here. I have this minus 2 over x plus 3. So the question is 5 over x plus 3 the same as 5? No, it's not. It's got that x plus 3 missing. That can't be my answer either. My answer, kind of through process of elimination, must be equal to D. And this is the right answer, D. 2 ways you can show that this is the right answer. Using division, whether it's synthetic division or polynomial long division is fine. But that's kind of a lot to do this problem. I think this process of elimination works better. What I would do probably is get rid of the 2 of these, and if you can't convince yourself whether C or D is the right answer, figure out what those are equal to, kind of work backwards. This is 5 over 1, which is 5 times x plus 3 over x plus 3 minus 17 over x plus 3. Right, now I have a common denominator, so this is just 5x plus 3 minus 17 all over x plus 3, which if I distribute this 5 through, I get 5x, and then 5 times 3 gives me 15, but when I subtract 17, I'm left with this negative 2 over x plus 3, which gets me back to the answer that I wanted. Do that same thing with C, you'll figure out that you don't get the same answer because it would be a lot like this, except instead of a 17 here, there'd be a 2. So you get a different answer. What your book, I'm guessing, what this test will tell you to do is probably like a polynomial long division thing. So you take x plus 3 over here, and then 5x, not a 5. Let's try again. That's a 5, x minus 2. And you do polynomial long division. So you say, all right, I could get 5 of these things in there. But if I multiply 5 times x plus 3, I get 5x plus 15. And now when I subtract, my x's go away, but negative 2 minus 15 is this negative 17. So what I get is that this number goes into this number 5 times with the remainder of negative 17. So what that tells me is that x plus 3, that 5x minus 2, 5x minus 2 over x plus 3 is equal to 5 that divided evenly plus some number of remainders. How many remainders? Negative 17 of these x plus 3 things. And this right here, once again, is the same thing that is given to us up in part D here. So there's a couple different ways you can solve this problem, and I'm going to stop this video here.